Assalamu alaikum. My name is Naima Khan. Imagine holding a material so powerful it can power cities, yet so dangerous it must be sealed away for thousands of years. Today, I will be diving into the fascinating and vital topic of testing radioactive wastes. This presentation will take you through the science, safety measures, and advanced technologies involved in the testing radioactive waste. We will explore what it is, why it matters, and how professionals ensure its safety managed. Let's begin this important journey. First, let's understand what radioactive waste really is. Radioactive waste is a material that emits radiation and is no longer useful. It mainly comes from nuclear reactors, hospitals, and research labs. It contains isotopes like cesium 137, strontium 90, iodine 131, and transuranic elements such as plutonium 239. These isotopes emit alpha, beta, and gamma radiations. Because of their long half-lives, they remain hazardous for years or even centuries, making careful testing and control essential. Now, let's look at the underlying science behind radioactive materials. Radioactive decay is a process where unstable atoms release radiation to become stable. The radiations include alpha, beta, and gamma radiations. This process is central to understanding the longevity and hazard of the radioactive materials. The half-life tells us how long it takes for half the atoms to decay, helping us predict long-term risk and determining safe storage durations. The materials behave differently in environment depending on their chemical form and solubility, influencing their mobility and environmental behavior. This determines how likely they are to leach to groundwater or soil. Ion exchange and precipitations are the key processes used to contain or remove radionuclides from liquid waste streams, often involving the use of specific resins or chemical reagents to bind or precipitate hazardous elements. The main goal of testing is to find out what exactly in the waste. We use radiometric methods like gamma spectroscopy to identify and measure the radioactive isotopes. This helps classify the waste, evaluate its hazard, and choose the safe disposal. To perform accurate testing, we need specialized equipments. The high purity germanium detector captures gamma radiations with great precision for identifying specific gamma energies. A multi-channel analyzer processes the data from the detector, converting them into an energy spectrum for analysis. Lead shielding reduces background interference and enhancing the signal to noise ratio during measurements. The sample and calibration standard are needed for accuracy. And safety gear like PPE, which includes lab gloves and a radiation dosimeter, are mandatory for personal safety and immediate repair. Before we even begin the test, safety comes first. Operators must wear lab coats and gloves and crucially a radiation dosimeter to monitor individual exposure levels. This step is vital for both personal and environmental protection. Next, we move into the calibration and precipitation and preparation of the sample. In the step 2, a known standard like European 152 is used to calibrate the detector, then records energy spectrum and calibrate the MCA. This ensures accurate identification of radionuclides by aligning measured gamma radiation energy with known values, creating a reliable baseline for subsequent sample analysis. Next, sample is prepared. Where the radioactive waste sample is transferred into a standardized geometric container, typically a marinelli beaker, and positioned it precisely in front of the detector. Encased within lead shielding, this standardization ensures repeatability and accuracy of measurements, eliminating variability due to sample placement and container shape. Now it's time to collect and analyze the data. In this step 4, we collect the gamma spectrum over a set period, typically ranging from 30 minutes to an hour, depending on the expected activity level. Longer acquisition times enhance the statistical accuracy, particularly for isotopes with very low activity, improving the precision of the overall analysis. In this step 5, software identifies the gamma peaks and quantifies isotope activity, helping us determine what isotopes are present and in what amount. Based on our analysis, we classify the waste. We categorize waste as low, intermediate, or high level. This classification guides storage, transport, and disposal decisions according to the safety standards. So, where is all this testing used in the real world? First of all, we will see in the nuclear power plants. In the nuclear power plants, it helps monitor radioactive levels in spent fuel and operational waste. It enables classification of waste as low level, intermediate, or high level. It assists in ensuring safety protocols and reducing radiation hazards for workers and the environment. In the environmental monitoring, it detects contamination of soil, groundwater, and air near nuclear facilities or accident sites. It also assesses radiological impact on ecosystems and public health. It also supports remediation efforts in the contaminated areas. In the nuclear medicine, it ensures safe disposal of radioactive isotopes used in diagnosis and therapy, including iodine 131 and technetium 99. It prevents the accidental exposure to patients, staff, and environment after medical procedures. It verifies decay rates before releasing waste into general waste streams. In the regulatory compliance, it confirms that handling and transportation storage of the radioactive waste meet national and international standards. It supports documentation and traceability for audits and legal purposes. It also helps maintain public trust and avoid legal or financial penalties. In the scientific research, it assists in studying radioactive decay chains for long life isotopes uranium 238, plutonium 239, etc. It enables research on long-term safety, storage safety such as deep geological repositories. It helps design more efficient contaminant methods and innovative waste treatment technologies. Finally, let's look at the future of the radioactive waste testing. We need real-time AI monitoring, better detection tools, and new contaminated materials. Global cooperation is also essential for setting unified safety standards. In conclusion, testing is vital for protecting health, the environment, and the future generations. By adhering to the meticulous procedures and strict safety standards, these practices are fundamental to support the nuclear safety, protecting our environment, and informing sound policy decisions for generations to come. Thank you for your attention. I hope this presentation gave you a meaningful insight into how we safely managing the radioactive waste using science and precision. Thank you. Allah Hafiz.